มีใครที่เป็นโรคกระดูกและข้อเจออาการทานยาจะหายปวดชาแต่ถ้าหยุดทานยาอาการปวดก็จะกลับมาและรุนแรงมากขึ้นเรื่อยๆควรใช้นมโอมาชัวตัวนี้ทันทีเพื่อส่วนที่เหลือของชีวิตไม่ต้องกังวลว่าจะกลับมาเป็นซ้ำอีกปลอดภัยประหยัดได้ผลเร็วโอมาชัวเป็นนมถั่วเจ้าแรกที่เชี่ยวชาญด้านการรักษาโรคกระดูกและข้อโดยใช้เทคโนโลยีการฟื้นฟูกระดูกและข้อของอเมริกาเพื่อช่วยลดอาการปวดและต้านการอักเสบเพียงดื่มวันละ2 แก้วเท่านั้นดื่มแล้วจะไม่ปวดหรือชาเวลาเดินหรือออกกำลังกายอีกต่อไปดื่มแล้วจะช่วยคลายความตึงของข้อยืดตัวลุกขึ้นนั่งลงได้สบายเคลื่อนไหวได้คล่องตัวป้องกันความเสื่อมและยืดอายุของกระดูกและข้อดื่มเท่าไหร่จะรู้สึกดีขึ้นเท่านั้นเลยผลิตภัณฑ์ได้รับการรับรองจาก FDA ว่าปลอดภัยไม่มีผลข้างเคียงต่อผู้ป่วยได้รับการประเมินโดยผู้คนนับล้านว่ามีประสิทธิภาพรวดเร็วสามารถใช้กับผู้ที่เป็นมังสวิรัติผู้ป่วยโรคเบาหวานและผู้ป่วยโรคหลอดเลือดหัวใจคุณลุงคุณป้าโทรสายด่วนบนหน้าจอเพื่อรับคำแนะนำฟรีจากผู้เชี่ยวชาญโปรโมชั่นพิเศษวันนี้ซื้อ3 กล่องแถม1 กล่องซื้อ5 กล่องแถม2 กล่องและพิเศษสุดรับส่วนลด 50% เมื่อซื้อ6 กล่องขึ้นไปอย่ารอช้าติดต่อสายด่วนบนหน้าจอเพื่อรับคำปรึกษาฟรีจากผู้เชี่ยวชาญทันทีเลย
หลังจากที่ฉันได้ใช้มาเป็นเวลา1 เดือนนะคะอาการเจ็บปวดฉันสังเกตว่าอาการเจ็บปวดของฉันตามข้อในตอนช่วงเช้าเนี่ยลดลงอย่างเห็นได้ชัดเลยค่ะ
หลังใช้สัปดาห์แรกรู้สึกอาการที่ชาที่มือและแขนหายไปการยืดและเหยียดดีขึ้นทำงานได้สะดวกขึ้นหิ้วของอะไรก็จับได้แน่นขึ้นตอนนี้ป้ายืดแขนสูงๆอย่างนี้ก็ไม่รู้สึกเจ็บอีกแล้วนะคะป้าต้องบอกว่าเห็นผลเร็วมากด้วยเทคโนโลยีใหม่จากอเมริกาส่วนประกอบทั้งหมดเสริมด้วยแคลเซียมและวิตามิน
ลุงใช้ผลิตภัณฑ์นมโอมาชัวเนี่ยมาได้ประมาณ1 สัปดาห์นะครับก็รู้สึกได้เลยนะครับว่าข้อต่อที่มือและเท้าเนี่ยมันนิ่มขึ้นเริ่มยืนขึ้นได้เองขยับจับสิ่งของต่างๆได้ลุงยังสามารถถือไม้กวาดเนี่ยนะฮะทำความสะอาดบ้านได้ด้วยรู้สึกได้เลยครับประหลาดใจจริงๆกับผลลัพธ์ที่รวดเร็วของผลิตภัณฑ์นี้
ผลิตภัณฑ์นมธัญพืชโอมาชัวเป็นผลิตภัณฑ์แรกของโลกที่ใช้โปรตีนจากพืช 100% เพื่อสนับสนุนการรักษาโรคข้อกระดูกซึ่งได้การรับรองจาก FDA สหรัฐอเมริกาจุดเด่นของโอมาชัวคือการผสมผสานตามอัตราส่วนทองคำระหว่างนาโนเคอร์คูมิน 5% พร้อมกับส่วนประกอบอื่นๆ เช่น MSM อะวาไทด์ซึ่งช่วยเพิ่มประสิทธิภาพในการลดความแข็งของข้อกระตุ้นการฟื้นฟูและการสร้างเนื้อเยื่อเพื่อกระดูกอ่อนอย่างรวดเร็วเพียงหลังจากใช้งานช่วงระยะเวลาสั้นๆโอมาชัวมีประสิทธิภาพในการดูแลผู้ป่วยโรคข้อกระดูกอย่างลึกซึ้งด้วยความสามารถในการลดอาการปวดข้อกระดูกอย่างรวดเร็วปรับปรุงการเคลื่อนไหวของร่างกายและป้องกันการเสื่อมโรคข้อกระดูกพรุนอย่างมีประสิทธิภาพเราคัดเลือกวัตถุดิบที่สมบูรณ์แบบที่สุดนำเข้าจากสหรัฐอเมริกาและผลิตภัณฑ์เทคโนโลยีทันสมัยที่สุดในปัจจุบันโดยกำจัดสิ่งเจือปนทั้งหมดและเก็บรักษาสารอาหารทั้งหมดไว้เท่านั้นสิ่งนี้ช่วยเพิ่มประสิทธิภาพของโอมาชัวได้หลายเท่าตัวการดื่มนมโอมาชัวอย่างสม่ำเสมอวันละ2 แก้วหลังจาก 2-3 เดือนจะทำให้การเคลื่อนไหวสะดวกและยืดหยุ่นมากขึ้นชะลอกระบวนการเสื่อมและโรคกระดูกพรุนทำให้ระบบกระดูกและข้อแข็งแรง
หลังจากดื่มกล่องที่3หมดนะคะก็รู้สึกว่าไม่มีอาการปวดหลังปวดคอปวดเข่าอีกเลยค่ะแถมยังมีผิวพรรณที่ดูสดใสขึ้นอีกด้วยก็ต้องทานคือเราไม่ต้องทานยาแผนปัจจุบันแล้วเพราะว่าทั้งขมแล้วก็ทำให้กระเพาะอาหารเสียหายแล้วแถมยังมีผลข้างเคียงทำลายตับและไตอีกมากมายเลยค่ะจริงๆแล้วก็ต้องขอบคุณโอเมชัวมากเลยนะคะเพราะได้ช่วยให้เราสามารถบอกลาความเจ็บปวดกระดูกและข้อที่เคยเป็นมาในระยะเวลาที่นานใครที่เจอสถานการณ์แบบเราก็คงเข้าใจว่าภาวะเนี้ยมันทรมานมากๆขึ้นอยู่กับการปวดแล้วก็อ่อนเพลียอยู่ตลอดเวลาถ้าไม่รักษาให้ทันท่วงทีเนี่ยข้อกระดูกที่เสื่อมสภาพมานานความเสี่ยงที่โรคจะกลายเป็นโรคเรื้อรังแล้วก็เกิดภาวะแทรกซ้อนอันตรายอื่นๆที่มีผลกระทบต่อชีวิตประจำวันอย่างรุนแรง
ตัวนี้ครับโอมาชัวทุกวันไม่มีขาดเลยครับผมรู้สึกโชคดีครับที่มีโอมาชัวเป็นเพื่อนร่วมทางครับผมอยากจะขอบคุณโอมาชัวที่ช่วยให้ผมหมดปัญหาเรื่องการปวดข้อปวดเข่าไปครับแล้วผมก็กลับมามีสุขภาพที่ปกติมีชีวิตที่สดใสครับผมอยากจะแนะนำทุกคนให้ใช้ผลิตภัณฑ์ตัวนี้ครับมันปลอดภัยไม่จำเป็นต้องไปโรงพยาบาล จากประสบการณ์ของผมนะครับผมยืนยันว่ามันดีจริงและได้ผลแน่นอนครับ
ถ้าฉันรู้จักกับนมกระดูกและข้อต่อโอมาชัวเร็วกว่านี้นะคะฉันคงไม่ต้องทุกข์ทรมานกับความเจ็บปวดและความยากลำบากในการเคลื่อนไหวของร่างกายขอขอบคุณนมโอมาชัวที่ช่วยปรับกระดูกและข้อต่อของฉันที่ทำให้ทำงานอย่างมีประสิทธิภาพและโรคเหล่านี้ก็ลดลงเป็นอย่างมากฉันขอแนะนำนะคะให้ผู้คนที่กำลังมีปัญหาเกี่ยวกับโรคกระดูกและข้อต่อลองมาใช้ผลิตภัณฑ์นี้ดูนะคะหากท่านใดมีความสนใจฝากเบอร์โทรไว้แล้วก็ทีมงานที่ศูนย์โอมาชัวเราจะติดต่อกับและให้คำปรึกษาฟรีนะคะช่วยให้คุณได้ค้นหาวิธีที่ดีที่สุดสำหรับสถานการณ์ของคุณนะคะนอกจากนี้กระบวนการใช้ผลิตภัณฑ์คุณจะได้รับการดูแลและสนับสนุนเต็มที่จากทีมงานดูแลสุขภาพและคอยติดตามรับฟังและให้คำปรึกษาอย่างละเอียดเพื่อให้แน่ใจว่าคุณจะได้รับประสบการณ์ที่ดีที่สุดและได้ผลลัพธ์ตามที่คาดหวังค่ะขอบคุณค่ะ
Built this oscillating edge sander from scratch. And you will never imagine the mechanism going on inside. Let me show you what it can do. Obviously, it's oscillating and can take different sized drums and the belt for sanding inner and outer contours. But what's always been bugging me with these machines is the drums and belts are this tall and most workpieces are not, resulting in only using the lower part of the sanding grid. Sure, the drums, I can just flip around, but the belt is directional. Flipping it around, you could catch the seam and rip it apart. So a key feature of my sander is a height preset. I can lower the whole mechanism down and use the upper part of the belt. Isn't that fantastic? It also works super smooth. Changing belts is done easily by flipping a lever, and the whole belt attachment comes off with this lever. Sweet! One feature I decided against is a tilting table. That's just inconvenient. On my machine, the belt tilts. Much more useful. It's effortless with this lever and clamped with a single knob. There's nothing on the other side, everything done from here, but it gets clamped on both sides. I'll show you later how that works. And the big dust collection part is out of the way in the back. That's everything from the outside. You will never believe how I made the oscillation mechanism inside. But first, let me tell you the stupid reason why I built this machine. Not because of the mechanism. A few years ago, I bought this sander with way too many sanding belts now sitting in storage. And I just wanted a better use for them. Really stupid, but that's the truth. Now, how do you approach such a project from scratch? Where to start? Well, I'll try to summarize. I wrote down a list of requirements with features I wanted the machine to have, like the tilting belt, the height preset, and so on. Then when designing at the computer, I put each feature into its own assembly. So this does the oscillation, this does the tilting, you get the idea. And wherever possible, I try to integrate multiple features into a single assembly. Sounds straightforward, but all that was the hardest part. I spent a lot of time designing. But then you can build assembly after assembly and bring them together. So let's get back in time when this didn't exist and begin with the oscillation mechanism. I've got this precision ground shaft which needs to move up and down together with the sanding drum. A common solution is a geared motor with a crank, but to me that's kind of boring. I wanted to couple the mechanism mechanically to the spinning shaft with a gear reduction. That should be interesting. From my machine specs, I need a gear reduction of 25:1, and I could do that with a worm gear drive. Every turn, the worm advances the gear by 1 tooth. It has 25 teeth, and I've got the right gear reduction. And then I can slide this into this housing, add a crank pin here, and there's the complete oscillation concept. It's a great concept with few parts, but 3D printed like this, it can't survive long term. This has to be metal and constantly lubricated, so I would need to find just the right one off the shelf or have it custom manufactured. That's not gonna happen. So another mechanism with a high gear reduction is a cycloidal drive. And if you ask yourself what that is, take a look at my logo. That's a cycloidal drive. Conceptually, it's simple. We have a housing with pins, the shaft with an eccentric cam, the cycloidal disc, and an output ring. The shaft goes in the housing with the cycloidal disc on top and when I spin it, it does this kind of motion. The output ring fits on top and turns that wobbly motion again into a smooth rotation. The gear reduction is the amount of teeth of the cycloidal disc, so in this case 9:1. This concept I'm sure I can make reliably lasting with simple off-the-shelf parts and 3D prints. And so now we've got a fast spinning shaft and a slow spinning gearbox, but no oscillation yet. On this concept, the output gear is oriented 90 degrees to the main shaft, making the crank possible. And I still need that for this one. Bevel gears, for example, could do that. But again, I don't see them lasting a long time. So what else could create oscillating motion? Let's start simple with this ramp shape. If I move this back and forth, you can see the intersection here is moving up and down. And I could pick that up with a bearing. Now let's mirror that ramp, and the result is one up and down motion without changing directions, or rather, one full oscillation. But how is this helpful? Well, when I wrap it around a cylinder and make it spin, I now get continuous oscillation. And what actually matters, this cylinder is the same orientation as my gearbox output and a single part. No need for bevel gears. So I think we have quite an elegant solution here and can get serious making the real version.
Getting serious means a lot of 3D CAD work. I modeled the entire assembly with every component before I ordered parts or started printing. But here we go. There are many printed parts, a few bearings, pins and screws, and machine parts, which I need right now, so I cut off pieces from some tubing. The longer bushing goes on first, with a washer and screw as an end stop that I have to play with, of course. Let's put that aside for now.
Now the gearbox housing. The pins this uses are actual steel pins that fit in these holes that I still need to ream.
The automatic compressed air comes in real handy here, removing the chips. The underside then gets a bunch of nuts pressed in, as well as a few on the inside.
I could have also used the CNC Kitchen melt-in threaded inserts, but what they don't have is a plastic lock ring, and since I'm expecting vibrations, I wanted that. This bearing is a light press fit in the center, and this ring goes on top, clamping it down, making this my fixed bearing. The large bearing fits around the housing, where it first slips down easily, and the last little bit is again a light press fit. And then insert all the pins. Next I need to make sure the cycloidal disc is sized correctly and moves freely in the housing. So when I put it in place, it should just drop down. But it doesn't, and I have to press it down. It does move, but it's pretty tough. I kinda expected this here, because I designed and printed this with no air gap, and when that's a real mechanical part, it's basically guaranteed to bind in some way. I need some amount of air gap in here, but just don't know how much exactly, so let's find out. I printed 5 discs with increasing play for testing, starting with 0.05. And it already drops down, but the movement is still kind of rough. 0.1. Yeah, that's a bit better, but there's still some places where it feels like it's binding. 0.15. Yeah, now it's getting better. 0.2. Yeah, that's great. And 0.3 is probably no improvement, just more play. Here you can see the play. This is 0.05 and this is 0.3. 0.2 seemed to be the sweet spot. Let's go with that.
A bearing gets pressed in, followed by steel bushings in all the holes, which came in an interesting packaging. And then a second one. But before the discs came another ring first. It has some holes to ream, nuts to press in, a center bearing, and then the output pins, because this is part of the gearbox output and it sits below the cycloidal discs. Now the parts can come together on the shaft. First the housing, then one of the spacers, and the output ring.
Next come the eccentric bushings that create the wobbly motion.
Their center hole needs to be reamed as well.
Then I have a feature in them which positions them opposite to each other like so. To fasten them on the shaft, there's a pocket for a little square nut and a tiny set screw. And now the disc. Wait. Ah, crap. I forgot to file slats on the shaft.
And disassembly is not as straightforward.
Yeah, at least I didn't forget to mark where to put the flats now.
Since the steel is hardened, I'm using a diamond file and it bites into the material well. But there has to be a more accurate way of doing this. I put 2 square blocks at the ends and this piece which holds the file parallel and at the right height. No need worrying about steady hands. But the real benefit is the second side, because I just need to flip the shaft and the second flat will be at a perfect 180 degrees to the first. Simple technique, but great results. The other flats are for later. Now I'm much more confident in the set screw and the cycloidal disc can go on top. I was really keen on testing, so let's do it.
This looks nice.
So now the second disc.
I need 2 discs because having only one wobbling around would vibrate. So having a second one opposite to the first one, the vibrations will cancel each other out. But I have to make sure the second disc is oriented correctly to the first one in the housing. Otherwise, these output holes won't line up with each other. Since I have 12 output holes and 25 teeth, this is not symmetrical and there's only one correct position. So I put a little notch at one of the holes to make this simple. Right here. Looking straight down, you can now see how the holes of both discs kind of do a circular motion around where the output pins will be.
So let's put them in.
That looks promising. The remaining 3 holes are for screws.
And after reaming the pinholes in the lid, it goes on.
On top now goes the actual gearbox output with matching holes, and on the outside there is the integrated ramp, which I made a lot smoother, and it also fits a bearing.
As usual by now, reaming the holes and pressing in a bearing, then the last spacer washer, and then assembling all the parts together. The screws hold everything together, but I have to tighten them by feeling, and this is my by feeling phase. Without context, this looks really stupid. And finally, a dust cover with an improvised labyrinth seal.
Oh yeah, that's the gearbox done. What a nice little compact unit, basically full enclosed and protected from dust, which is nice. It's super smooth. I can't really feel resistance other than the 6 fresh bearings. And what you might not expect is this is back drivable, which means it works when I spin it here or here. That's cool. Just too bad you can't really see the inside now working. Let's fix that. There you go. I cut it open. Let's see it in action.
So for this short sequence, I had to disassemble everything again, but this then at least allowed me to add grease when reassembling.
But still, can this survive long term? Because it will run a lot. Well, I'm confident because all the motion is either done by bearings, metal on metal, or at least well-lubricated plastic on metal contact. And even if that's still not enough, I've got one more trick up my sleeve. Because thanks to the sponsor of this video, JLC 3DP, I've got all gearbox parts and some more for later printed from nylon, a much tougher and more suited material than PLA.
Other manufacturers also know that. For example, this gear in my planar gearbox is also made from nylon. While we're in here, let's clean it.
And look at the print quality. That's just nice.
Much better than what I could achieve. And ordering these parts from JLC is pretty simple. If I print them myself, I export the 3D model and import it into my slicer software. For the order, I just upload the same file to JLC 3DP. Here I could then choose the 3D printing technology, in my case SLS with nylon, the amount, and I instantly get a quote.
For example, 2 cycloidal discs are just $6.50.
Just like my own parts, all these of course also need some reaming before assembly. But then they pretty much go together the exact same way.
And there it works. Nice. The heart of my machine. If you need custom parts, give JLC 3DP a try. Their printing service starts at 30 cents. Their CNC machining service starts at $8. And if you use my link in the description, you can get a $60 coupon. But for now, let's disassemble it again, because until the final assembly, I want to stick with my parts, because I of course want to see if they work. The next part that goes on the shaft is the pulley.
It's made from the pulley and the pulley support and starts out as this chunk of aluminum. This first gets a facing cut and then turned to size with a few roughing and finishing passes and a chamfer. It's a non-critical dimension, but still nice when you hit the 45mm exactly. I used a 3D printed template for transferring the hole locations and then cut the piece off, but forgot to record. It could have looked like this. Except the diameter is too large for my tools, so the last bit is for the hacksaw. A quick jaw swap to clean up the second face, and then heading to the drill press for the threaded holes. Spot drilling, chamfering, and threading. Standard procedure. For the set screw hole, I installed 2 screws that position the piece correctly in the vise, and with the ruler method, I made sure the part is centered. Then I carefully spot face with an end mill and do the rest. For now, this piece is done. The pulley starts as a scrap of polyethylene sheet, which I placed on the CNC router to cut the screw holes and a slightly oversized circle. Cut out, it goes in the chuck where I marked the rough size of a pocket, which I turned to a snug fit with the pulley support, followed by chamfers and removing this material, which creates very fluffy shavings. Then the pulley support goes back in the chuck where I faced it one more time and then screwed on the pulley with a dab of Loctite on the bolts. I turned the diameter to size and sharpied it black to better see what comes next. Finding the edge with the tool, move it to the center, scratch the surface and zero the dial. Then plunging to a certain depth, creating the V grooves for the belt and breaking the sharp edges. The last feature is a precise center hole, which I drilled and then carefully turned to size. It took many passes, but I hit my target and the result is this.
Ah, perfect. Alright, next comes the upper bearing block.
The upper bearing sees more of the load when I'm pushing against the sanding drum, so I made the bearing housing from aluminum. Here I marked the side centers, which helped me to position the piece at the correct location on the machine bed. There, I first machined the holes that align with my hole grid, so I can use 2 bolts to hold it down, and then I let the machine go to work. The finishing pass is really satisfying, as well as the chamfer. Turned out really well, but right now the bearing doesn't fit, because the CNC is not accurate enough for a bearing seat. And I want to turn that, so somehow I need to hold it on the lathe. I've got some round offcuts from a laser that should work. I marked the center and the whole spacing of the 2 hold-down holes, which I then quickly turned into threads. With a magnet on each jaw, the plate has just a little bit of stick out. I face it by leaving some material at the center, and after about 1mm, I turn it to a nice fit with the aluminum. That puts it in the perfect center and I can hold it again with bolts. I left myself about 1mm of material so I can do multiple passes and get it accurate. And I think that paid off. The result is spot on. Then turning the hole to final depth. At the drill press, I drilled and tapped the outer holes to M6 and the inner holes to M3. But since they are blind holes, I finished the threads with a drill and a low clutch setting.
The bearing nose should be a light press fit. And it's not. Oh, fuck.
Turns out the bearing is also slightly undersized, which I should have measured before. But at least I can now try out a trick my dad told me. A layer of Sharpie. It's a few microns thick and should solve the problem.
Oh yeah. That's a press fit now. Nice.
And the 6 screws hold it in place.
The last part that goes on the shaft is the drive block thingy that engages with the sanding drums.
It's straightforward and similar to the pulley support. I face and turn some stock to size so it again fits the template, chamfer it and cut it off. This time with recording it. Flipped around, I face it to length and then drilled and turned the hole to the same fit as the pulley. Then transferring the hole positions, drill and ream them to size and depth, and hammer in some pins, which will engage with the sanding drums. They also line the part in the vise for the M6 set screw hole.
Very nice. Everything is mounted, but it's far from being a finished sander. This needs to be mounted in something, and I call that the sled.
The sled basically is a wooden box where all parts have different features cut into them, and after a bunch of toolpath programming and flattening the CNC bed, I can begin. The workhorses are these single flute bits in different diameters. They allow me to take aggressive cuts and remove a lot of material. But first I have to prepare my material. Some 18mm thick birch plywood, which I cut into roughly oversized pieces, and then cut a shallow groove all around for my hold-down clamps. This gives me access to the whole surface for machining. But mostly the stock material isn't flat to begin with, so I shim the gaps to not bend apart with the clamps. I then cut the various holes and other features into the part, followed by the outer contour to about half the depth. Then I switch to the flattening bit to make the surface flat and also cut away all the burrs from previous operations. And then the program waits for me to switch to screws to finish the outer contour. And like this, I cut all the parts. Some I also just tapped. And of course, I also had to crash into the shim, destroying this brand new bit. At least I can continue, so I removed all the bigger chunks, flush trimmed the edges, and made new grooves for the second side. I then used pins to precisely position the parts for the second side. That works because I have the same whole layout in Fusion 360, so the software position and the real position match, and I don't even have to probe the parts. Most of the second side operations are holds, chamfers and big chamfers, and flattening to thickness. Basically the same for every part. And there are all of them finished.
And none of these parts are sanded, but by using the right techniques and especially order of operations, I get these clean and sharp edges everywhere on both sides. Let's check the fit. Ah, beautiful.
Before assembly, I inserted a few nuts and some steel pieces that I first needed to make. However, straightforward. They will be used later.
I'll do the assembly here on the table saw, because I know this is a flat surface, starting with the back and middle piece. The bottom edge needs to be flush, and then I can transfer the holes.
All these screw joints got a clearance hole using the existing holes as a guide, then a pilot hole, and then a screw. That way the drill bit doesn't wander in the plywood edge.
Then the top plate flush with this edge, the left and right side.
But they needed to be clamped in position.
Lastly, this bottom piece, but it seems to be just a hair too wide. So that's the sled skeleton almost complete, and because of the way I designed this, all the pieces are kind of squaring up each other, making this a square block all around.
With it all together, I could remove a few screws again and replace them with the dowels to make it a more permanent connection. Next came two pieces for the motor mount, except they didn't require the CNC router, and then they got bolted on with the nuts I previously installed. Then I made these angled pieces that close the gaps between the top and back plate and glued them in place. With the glue dry, I flush trimmed all the dowels and then cut a large bevel, which is for clearance when tilting.
That's the finished sled frame. Let's add components to it. The gearbox with belt goes in here, where the housing gets bolted to the bottom, the bearing block to the top, and the motor goes here. Yeah, what motor?
I've prepared something for that.
I picked up this crappy little table saw for free from the garbage, where it belongs. I mean, I'm terrified of this as a table saw. but it has a nice little motor.
I just need to free it from all this terribly dangerous table saw crap.
And there it is, freed from the pile of scrap metal. Nice and quiet, 700 watts and 2800 RPM. That's great. The capacitor and wiring I'll mount elsewhere, so the motor really is as compact as possible. Something strange though is this. A significant rubbing noise coming from the back. So I took off the back cover and couldn't believe it. There are two pieces on the fan that are intentionally rubbing on the housing. Why? Was this supposed to be a motor brake for the table saw? I don't know. Let me know what you think in the comments, but this will go. Even spring-loaded.
Now right here on the shaft needs to be a flat spot for the pulley set screw. I could hold the shaft in place with vice grips and use a similar file contraption as before. Only this time the shaft isn't hardened, so I could use a normal file.
The rest of the shaft is too long and I also don't need it, so off it comes.
I then let it spin to clean the end and chamfer it before I started working on the motor mounting brackets. I cut them from some steel flat stock. Another job for the big ass file, getting the length right until they fit in the sled. Then I transferred hole positions, punched them and drilled them. For the slots, I drilled multiple holes that slightly overlap each other, so I could fit a jigsaw blade to remove material, so I could fit a Dremel to remove material, so I could fit a file to finish the slots. Not my best work, but the slots work and that's what counts. Then I transferred hole positions again, drilled pilot holes and added screws. I couldn't reach the top screws, not even with a driver bit in pliers, so I opened up these holes and used hex head screws. Now that's a solid mount to bolt the motor to.
Well, I've got a problem. I cannot get these back screws installed. There's just so little space, and I knew this would be difficult. I can get them in place, but then just can't get the thread started and the screw jumps around. And the pulley isn't even installed yet. I don't want to drill access holes in the top because I wanted that closed off. Yeah, but I have an idea that might work.
With a threaded piece, I can hold the bolts in the lathe chuck and work on the threads. I had to shorten them a bit and then remove the threads of the first couple millimeters.
So now the screw can fit in the hole and stays in place, making it much simpler getting the thread started.
Then I also realized I could remove the front support for more access.
Nice. And the threads are in. Alright, now I know how I can mount the motor and can continue with making the pulley.
It's relatively simple and starts from this piece of aluminum from before. First facing, turning the major outer diameter and the step to size. Then I again mark the surface to easier locate the edge and the starting depth, and then turned the 3 slots just like before. Here I also broke the sharp edges with a file. And lastly comes the hole. I first removed most of the material with a drill bit, then measured the actual motor shaft and turned the matching bore. Checking with the motor, and that's good. Flipped around, I could part off the rest, or at least that was the plan. Luckily, only a static damage and I could continue. Everything left is facing to length, turning the second step, deburring the hole, and making the threaded hole for the set screw.
For the wiring, I 3D printed this custom lid. It fits one of these cable clamps. The capacitor has its place here, with the wiring going internal through this hole. And when it's assembled, the hole will line up with this one that I need to open up.
Not only that, but also cutting through the top. Then I finished up the wiring, gave it a test spin, and closed the lid. That turned out nice. Another addition before testing the gearbox with the motor are 2 bearings on top of the gearbox output. They are the axial support and will take load away from the other gearbox bearings. But having just a plain bearings on top didn't work so well and was wearing the surface quickly, so I printed these cover parts from TPU, turned and chamfered them, and pressed the bearings into them, like wheels. That's better. And back to the motor. I spent some time installing it back in the sled, got the belt on the pulleys, and tensioned it. It's also important for the pulleys to be aligned to each other, which I could adjust and check with a bore gauge.
And now it's ready for the first power test. It works. Woohoo!
What a strangely soothing and satisfying motion.
Very nice so far. Now I will remove everything again, because moving forward it's easier when there are less parts and weight. For the sliding hardware I'll be using a linear rail with 2 blocks, because this set is with just about $40 pretty unbeatable. The blocks have 2 precise surfaces, one where it gets mounted and one here that runs parallel to the rail. And to get them aligned on my sled, I've machined 2 holes for pins where I can slide them against. Mounting them to wood is